timely topic, I would say, quantum machine learning. Of course, closely related to a recent Nobel Prize. And also a second person I want to introduce is Rafael Chavez. He's one of the organizers, so if you want to talk to him, he's here this week. Okay, then Marco, it's your turn.
All right, thank you very much. First of all, eu estou muito agradecido com os organizadores. Para mim é muito importante fazer ciência na Latinoamérica, então eu acho que isto é muito importante para todos. So I'm really grateful to be here. I really love Brazil, and I'm so happy to be here. I've had a chance to talk to many of you over the past week, and I think that it's a great community that has been built here. So today, I'm going to be presenting some of the work that we've been doing on the prospects and challenges for quantum machine learning. So it's going to be today, tomorrow, and the day after the first session. So this is going to be divided into 3 parts. Today is going to be mostly slides. I'm just going to be talking and giving an introduction to quantum machine learning, some of the promises of this architecture, and then we're going to explore some of the difficulties that can exist when using this technology. For the 2 sessions thereafter, we're going to use essentially old Blackboard. My main idea is to give a crash course on group and representation theoretical tools and give you some ideas of how it is that now we're working on dequantizing many quantum machine learning models and showing that actually everything that they're doing, a classical computer can do. So this is going to include 1 class for Lie algebraic simulations and 1 class for Weingarten calculus. I think I'm trying to pack way too much into 3 classes. So if we just get through 2 of them, I'm going to be happy, but I'm going to try to get you to the point where at least the basics of all 3 are covered. I'm going to give you a disclaimer. First of all, this talk is going to be very opinionated, and this is by design. I'm going to try to be very doubtful of whether quantum machine learning can work, and the idea is to try to inspire you to prove me wrong. But we want to do this the right way. Also, this talk is going to have memes. A lot of memes. Like, really, it's too many memes. I'm not sure how my managers approve my talks because they have way too many memes. Okay, so the beginning of this talk is going to be about quantum machine learning. And here, I'm essentially going to try to be a salesperson. I'm going to try to sell you this technology as the next revolutionary breakthrough. So we've all heard about quantum machine learning, or at least I think we all have. Who has heard about quantum machine learning? Okay, perfect. This is great because that's going to save me some time. And also, Daniel already did a great job of introducing some of the basics. So at their core, the idea is that we have this technology, machine learning, which is just physics at the end of the day, as we now know from the Nobel Prize, that has been extremely successful. And it's been able to change essentially how we do science across the board. Pretty much anything that you do, nowadays there's going to have a component of machine learning. And we also know that quantum computers are this emergent technology that can solve problems that we think classical computers cannot solve, like factoring, or problems that we know classical computers cannot solve, like quantum simulations. And of course, the idea is, well, I have classical machine learning, I have quantum machine learning, let's try to combine them and use quantum computers to process and learn from data. And this is what people usually refer to quantum machine learning. And of course, the hope is that by exploiting quantum properties, this is kind of like a vague statement, we can outperform classical models in learning tasks. And for me, the only caveat that I might say here, where maybe this is something that I really believe in, is that if we have quantum data, and I'm going to explain what I mean by this, maybe we can really get some computational advantage. So what is the generic schematic diagram of a quantum machine learning model? So what we're going to try to do is we're going to have a task of interest which we don't know how to solve. And we cannot just write a program that is going to solve this. So we cannot apply traditional programming. And what we're going to do is we're going to use the learning methodology of classical machine learning, where we encode the problem into a learning or optimization task. So as Daniel was saying, you have this ground state, this molecule, and you want to try to get its ground state, you're going to try to parameterize a model, define a loss function, and optimize it to solve the task. And usually, this is pretty much the paradigm that we're going to have, is this idea that our input to our problem might be a training set if we have data. We might have a cost function defined as the expectation value of some Hamiltonian of interest. We might have a parameterized quantum circuit. And what we're going to do is we're going to use the quantum computer to try to process some information that we hopefully couldn't do otherwise classically. And a little bit of the hope for quantum machine learning is that we can use the exponentially large feature space offered by the quantum Hilbert space to process information. And we know that embedding data into higher dimensional spaces is something that is useful in classical machine learning. And then once we've computed some quantities that are maybe hard to compute, we're going to loop them into a classical optimizer. We're going to define an optimization loss function that we're going to try to minimize or maximize. And we're going to use the power of classical optimizers to update our model's parameters. These are usually going to be some set of parameterized gates in a circuit. And we're going to do this loop until we get convergence. And maybe at the end of the day, we get a quantum state, the ground state of our molecule, or maybe we want a quantum operator that can do some discrimination of data points in a data set. And something that I'm going to be basing myself on throughout this talk and throughout the next 2 days is that in the quantum computer, we're going to measure quantities that look like this, which are essentially take a state, evolve it through a parameterized quantum circuit, which we're just going to write as a unitary U that depends on a set of trainable parameters, theta, and then we're going to measure expectation values of some operators. Of course, you can do classical post-processing on this. You can combine many of those. You can define mean squared error loss functions or whatnot, but at their core, I'm going to be focusing on quantities that look like this. I think that this covers pretty much most of the cases of interest. Now, this paradigm definitely has gotten a lot of hype, like a lot of hype. And at this part of the tutorial, as I said, I'm going to be a salesperson. And I'm going to try to explain the basic principles of quantum machine learning through the 5 Ws, who, what, where, when, and why. And what we're going to try to do is define the basic pipeline of how to build a quantum machine learning model, just so that we can see that it's actually fairly easy. From my perspective, we have the learning curve of time versus how hard this is going to be. And I'm going to try to get you to this point where you're like, oh, we can solve any problem with quantum machine learning. And then I'm going to leave you to this point on your own. So where can quantum machine learning be used? So this paradigm has essentially been proposed for essentially every single task. If we want to solve linear systems equations, factoring, which are problems that we know quantum computers can do, we can do combinatorial optimization. If you know about the QAOA algorithm, we can find ground states via VQE. We can do dynamical simulations, find new quantum error correction codes. We can do machine learning, like classifiers and also generative models. So, it's pretty much every problem that you can think can somehow be cast into a quantum machine learning model. Next, what we're going to do is we're just going to focus on supervised learning, just for simplicity. And what we're going to think about here is that we have some data set. It might be classical or it might be quantum. For classical data set, we assume that it's going to be some real valued vector xi. And what we're going to try to do is learn that these have associated a label. In this case, X can be associated with a label that is either cat or dog. And I found that if you want to publish papers with pictures of animals, you better make sure that you own those rights, because otherwise it can be a problem. So those two are my cats. So from here, what we're going to try to do is we want to try to put our data somehow into the quantum computer, so encode classical data into a quantum state, and then we're either going to use a quantum neural network or a quantum kernel to try to do the classification and try to do the prediction. In the case of quantum data, we will assume that this already lives inside of a quantum computer. So maybe you've already done your VQE, you found a bunch of ground states, and you want to try to predict whether there's superconducting or metallic. So you would do the same thing. You would train a model that will try to do the prediction. We will also focus very much on quantum neural networks. So all of this is setting the stage from this very broad area of quantum machine learning to the specific subset that we're going to be talking about today. But interestingly, as we will see, the line between what people call neural networks and kernels in classical machine learning gets very blurred at a quantum level. And there's this really nice perspective article by Maria Schul discussing this. So let's consider an example, because you might be wondering, okay, so how do we actually go about doing this? And let's think about this extremely simple classification problem where my data are just real numbers. Let me assume that they're just taking some values between minus pi and pi. there's some arbitrary cutoff that I'm going to define at pi/2, and I'm going to say all the numbers that are here, I'm going to assign label 1, the ones in the middle, label 0, and the ones here, label 1. Now, I'm a human. I'm extremely lazy. I want to do the classification by just drawing a line and say everything to the right of this line is going to be one class, everything to the left of this line is going to be another class. Well, it's not too hard to see that we can't really do this. Wherever we draw a line, there's always going to be some error that is incurred. So how do people solve this in classical machine learning, just to get an idea of what people are already doing? So one approach is this idea of the kernel trick, which is take data and put it into a higher dimensional space. And here what we can do is we can take our data x, and we can now map it to R2, a plane, where the second coordinate is just x squared. And what we can see now is that our data lives over this parabola, and we can just fit a line that will do the classification. So now everything that is above the line is one class, everything that is below this line is another class. So kernel trick, put in a higher dimensional space. Support vector machine just means train and find the best classifying hyperplane. Now, this is maybe not so exciting. What people like is neural networks. Oh, this is from another talk, so forget about this. So in neural networks, what do we do? And for people that are not familiar with deep learning and neural networks, if you understand this picture and this, you're going to have almost full proficiency in classical machine learning. So this, I'm going to call this a neuron. It's just a real number. And I'm going to take this and send it through other neurons that take inputs and have outputs. So for instance, F1 just takes the real valued input x, multiplies by a weight, adds a bias, and outputs a number that has gone through a nonlinear function like a sigmoid. F2 does the same. And then we take F3, which has two inputs, so the output of F1, the output of F2, and then just output another real number. And what we can do is we can train those weights and biases, and we can actually do a pretty good classification with just a couple of optimization steps. So this is essentially classical machine learning 101 in a nutshell. And this works, you know. Again, we've seen this time and time again. So the question is, can we try to do the same thing with quantum machine learning? How would we solve the exact same problem if we have access to a quantum computer? So the first thing that we want to do, as we've already said, is that we have real value data. We need to put it inside of quantum states. So we're going to have to do some encoding, and we're going to have to also decide how to extract information from that quantum computer, which we're going to do by measuring the expectation value of the Z operator. So this is the setting that I'm going to be working on. And I'm going to predict labels by this function right here. This is just a subtlety because the labels have to be 0 or 1, not continuous numbers like this, but, you know, again, subtleties. So how do I go about encoding? I can just start with some fiduciary state, like the plus state, which is easy to prepare. And then I take a classical data point, and I just put it in a rotation around the y-axis like this. So what you can see now is that we're taking our data, and we're embedding it in a higher dimensional space. This is very reminiscent of the kernel trick, because we are now living in a two-dimensional space, which is the surface of the Bloch sphere. After we've done this, we know that our data is going to look like this, and we know that measuring the expectation value of Z just means checking if I'm in the northern hemisphere or the southern hemisphere. So this encoding wasn't really quite good. I can't do my classification like I wanted to do it. So what I'm going to do now is I'm going to try to process coherently the information at the quantum level by sending my states through a quantum neural network, which is nothing more than another parametrized quantum circuit, which is going to be a parametrized rotation around the y-axis. Then, again, because I need to estimate the expectation value of Z, and we have to do this via measurements, I'm going to compute this with a frequentist approach, which is the number of times I got 0 minus the number of times I got 1 out of n shots. And this is going to be very, very important. So always keep in mind that we can only extract information from quantum computers via measurements. This might seem like an obvious statement, but you have no idea how many papers are out there that are training quantum models with no shots, no finite samples, since you have infinite access to your quantum model. So this is extremely important. Now we define a loss function, like the mean squared error, to try to see how our test data looks with respect to are there true labels. We train the models, and we can do perfect classification here. So with this, you know, we've now done this a la neural networks. We're processing information. We're multiplying, doing linear operations, and trying to learn something from those. Let me get you the mic, because I see a question here. Hello.
You said the slide, I think 3 or 4 slides was at the beginning of the presentation. You have like to train the algorithm in a classical computer.
Yes.
What does this is a statement, or like you think that this will change with the advance of the technology that we have?
So in principle, this paradigm is independent of the technology, because you can get this guy, you can just feed this into any classical optimizer that is going to give you the next set of parameters theta. Like here, every time that I update my parameters theta, I get my cost function down. So I don't think this is dependent on the technology. This is just how the general framework is defined.
Okay, the second question is, you get the loss function and the train of the model.
Yes.
You get it to every single time that you run the algorithm, or like you run the algorithm n times and you start to train it, and you train as long as you want.
So in general, you need to run this procedure of estimating the cost function via measurements every single time you update theta. And then you just keep running it until you hit some convergence criteria. You might say, I want my loss function to not have changed by more than epsilon after this many steps, and then that is just stopping criteria.
Okay, thank you.
Okay, so with this paradigm, this is all very nice and pretty, and we can just see that the basic pipeline that we've done is how did we build this quantum neural network. We first embedded data inside of a quantum computer. We defined some loss function. There might be some properties that we want to try this loss function to satisfy. We picked some ansatz or some choice for the parameterized quantum circuit, which we call a quantum neural network. And then we've picked some classical optimizer, and we've managed to solve our problems. Now, this shouldn't be surprising to anyone, and this is why I'm not going to spend too much time here, because this was already in Daniel's talk. Exactly the same series of steps that I've just given you to do the classification of this classical data via machine learning is exactly the same sequence of steps that we've used for VQE. So, what can we do with this? It's such an exciting paradigm. It's very easy to implement. So why don't we use it to classify classical data? Why don't we just classify zeros from ones? We can do this with fairly good accuracy, 97%, and this can be improved. This was just testing something very simple on 8 qubits with a quantum convolutional neural network. These are details. We can discuss about them later, but I don't want to get boggled in them. Maybe you're saying, like, OK, maybe classifying zeros and ones is too easy. I want to classify shirts from pants. Well, we can also do this. And you're like, maybe this is still too easy. I want my quantum neural network to be a part of a self-driving car. So why don't we just classify road signs for a model that will use quantum to drive in Germany? And you can absolutely do this, and this will work. And all of these are just examples of what you can do if you take classical data and you put it in a quantum computer. And what about quantum data? Why don't we just use this paradigm to classify phases of matter? So again, by quantum data, I'll just refer to states that already live in some Hilbert space. So for instance, Daniel already had this exercise in the hackathon, which was prepare the ground states of the Ising model. Well, the Ising model, which takes this form, is really nice because it allows us to study properties of interacting magnets, and this is paradigmatic model in statistical mechanics. And this model will exhibit a phase transition. This is not a true phase transition. It's a finite size system. It's just a level crossing. Please don't say that the Ising model has a phase transition, but we'll just say that it does have a phase transition for now, when my magnetic field or the relationship between the coupling and magnetic field is equal to 1. So you might just say, oh, maybe I just want to use Daniel's pipeline, combine it with something else, and have an algorithm that classifies phases of matter. So we would like to create a data set from the Ising model and classify them using a quantum neural network. You can think about a pipeline that kind of looks like this. We fix a value of the couplings. We use VQE to train a parameterized circuit that is going to give us the ground states of the VQE model. Then we're going to assign a label depending on the phase that it belongs to. And then Once we have this data set, we're going to send this through another quantum neural network that we're going to parameterize to try to do the classification. And again, all of this will follow this exact same pipeline. Creating the data set, we need to pick some ansatz. So you're like, OK, what should I use for my parameterized quantum circuit? So you do some literature search, and you find that there's this really nice ansatz called the Hamiltonian variational ansatz, which tells you, if you're trying to find the ground state of this Hamiltonian, why don't you just pick a unitary that is just the exponential of the terms in your ground state? For the Ising model, this will kind of look like this. Did you have a question, or should I? OK. Now, you might be saying, OK, but this is just an ansatz. Does it really work or not? Who here has heard about Barren plateaus by show of hands? OK. So some people have. You might have heard that there is this problem of loss functions being exponentially concentrated. You don't have gradients. So you're like, before I commit to this, let me check if it has Barren plateaus. Oh, you check, and it doesn't have Barren plateaus. The gradients only decay polynomially with n. So then you're like, OK, I'm very happy. I'm going to use this. And I define my cost function, which is just the ground state of this model. And I'm going to prepare the data set. Now, how do I classify? I need to pick an ansatz. So you're like, how do I classify this? Maybe I use this thing called quantum convolutional neural network. It's very used in the literature. I'm going to explain this in detail as one of the other classes. So for now, just think about this as it's a model where you process information, reduce the number of qubits via tracing out or measurements, process information, and so on, so that at the output, you just have the information compressed in a small number of qubits. Again, you might be like, Barren plateaus. Does this have Barren plateaus? Well, it doesn't. It's just polynomially decaying. And this is something that we've managed to prove rigorously. So now you just define your cost function, like the mean squared error. You do your training, and you can get 100% classification accuracy on classifying the ground states of the Ising model. So I think at this point, you're almost here. Full quantum machine learning proficiency. Now it's just a thing about cranking the notch, getting so many papers out. And we've been working on quantum machine learning models and variational algorithms for, I think, the better part of 7 going into 8 years now, at least since VQE was proposed in 2018. And there's so many papers about working with this paradigm. If this I updated over the weekend, if you see the number of papers working in VQE, this beautiful exponential going up. QAOA for solving combinatorial optimization problems follows the same trend. And QML is just off the charts. Last year, there were around 400 papers on QML alone. And one might be wondering, OK, so after all of this, we must have a quantum advantage. Well, not really. I don't think we're quite there yet. And I don't think anyone has proven that this model can give a quantum advantage. So why this? Why do we see these curves going up? So for one thing, and I'm going to quote a colleague of mine, Zoe Holmes, and she said this one sentence that I really like, which is that, in a way, I think that variational algorithms have democratized quantum computing, in the sense that it's very easy to do variational. It has promise across multiple disciplines. There's very easy access to it, a very easy learning curve. You just need to know a little bit of linear algebra and Python, and you're ready to hit the ground running with variational algorithms. If you wanted to, say, maybe work on optimizing better trotarizations for simulation algorithms, well, this is going to require likely a lot of knowledge of quantum information, group theory, and physics. So there is definitely a gap between this kind of like machine learning approach to algorithms and standard programming approach to algorithms. But of course, if something seems too good to be true, it probably is, because this paradigm has so many issues that we will discuss now. And of course, for me, the main concern is that we just have this quantum computing paradigm, and we're just kind of like slapping machine learning in it and calling this quantum machine learning. What's really funny about this meme nowadays is that it is Z2 symmetric. People just have their machine learning algorithm slapping a little bit of quantum in it and calling it a day. So I think this is one of the reasons why the paper trend has gone up, is because both communities are just tackling quantum machine learning. And again, if something seems too good to be true, it probably is. And you might be saying, well, classical machine learning, we just test stuff and they work. So you don't have provable guarantees. You don't know that an algorithm is going to converge or that a solution exists. So what up? Why don't we do the same thing with quantum? Well, the thing about classical is that you can just test your model at a toy model problem. It works. Then you go to realistic problems, and it keeps working. This is something that we just cannot do with quantum machine learning because we don't have the devices to test these algorithms at scale, and their simulation is just really expensive to do. So while we've shown that quantum machine learning maybe has some heuristic success at small problem sizes, we don't know how they're going to perform at the large scale. And in a lot of cases, you can actually train a model from 8 to 16 qubits, but you haven't seen that point where it's going to just become too hard because you haven't seen the exponential scalings. Exponential and polynomial scaling look very similar for small n. And this can be a very big issue that we're just not seeing. So for us, I think that the approach that we've taken towards this is try to identify all the problems that quantum machine learning can have, Barren plateaus, local minima, ansatz that don't contain solutions within their search space, how to encode, the problem of noise and whatnot. And we're going to try to find a quantum advantage via process of elimination. So that means, OK, let us identify the things that we shouldn't do. Because if we can rigorously prove that we shouldn't do all of these things, then at least we know that we shouldn't be trying to bang our heads with these, even if they work at the small scale. And for me personally, over the past years, I've been working on this problem of Barren plateaus. So Barren plateaus, as we'll see, are just essentially a problem about precision in quantum computers. So imagine that you have this single qubit state, and I ask the question, what is the probability that this state is, when you measure, you get the 0 state? And you have to remember, again, we can only extract information from quantum computers via measurements, and quantum computers are probabilistic. So if you ask a theorist like myself, I would be like, oh, it's easy. Just compute the projector, the trace, the Hilbert-Schmidt inner product with the projector into the 0 state, and that's it. But if you go to a lab, what you're going to have to do is the best thing that you can do is just measure big n times and do, again, a frequentist approach, where we're just going to estimate this probability by the number of times I got 0, by the number of total times that I measured. But this comes at the price of statistical uncertainty. Whenever you estimate a probability this way, it's going to have a statistical uncertainty, or your statistical precision is going to be of the order 1/√n. So what is a non-mathematical definition of Barren plateaus? Which is that your cost function values are going to be, in average, or across most of the landscape, exponentially concentrated with the system size. So what does this mean? That if I take 2 points in the landscape, and I want to try to compare the point at parameters A and the point at parameters B, they might be close, they might be far. In average, this is going to be of the order 1/2 to the n, where n is the number of qubits that I'm working on. So if you're trying to train 4 qubits and you have a Barren plateau, then you need to be able to tell apart differences in cost functions of the order of 0.06, which you can actually do with just 256 shots. So again, you have a Barren plateau, but because you're working in a very small problem size, you don't even realize it. You might be using like 10,000 shots here, so complete overkill. But now, if you have 20 qubits, your differences are of the order of 9.5 times 10 to the minus 7, and you're going to need 1.1 times 10 to the 12 shots, or 1 trillion shots. And here you can start to see why this is going to become a problem. Because you're not going to have statistical certainty. You're going to measure your loss function at point A, at point B, and you're going to think, OK, this one is lower. But actually, no, it's just statistical fluctuations that you're seeing. It's not the true landscape. And if you don't care about math, just think about money. And the problem is that measurements are a true resource in quantum computers. So if you take Amazon bracket, you see the average price of how much it takes to make one measurement in a quantum computer per average. To do one optimization step in a Barren plateau landscape, to be able to tell 2 points apart, you're going to need $10 billion US. So yeah, this is non-scalable any way that you look at it. This is just a tremendous problem. And for people that might be wondering, this is not a problem of the optimization method that I use. You might be using gradient-based optimization, gradient-free optimization, Hessian, quantum Fisher information matrix. Nothing works. This we've guaranteed. And we've guaranteed because every time that we put out a paper on Barren plateau, someone was like, oh, but what happens if I use this method? Then we go and we prove that that also doesn't work. Then someone else, what about this method? Then we go and we prove that it doesn't work. But in general, if you have a Barren plateau, we should just kind of like forget about trying to train our model in a Barren plateau. So there are many sources of Barren plateaus, which I think we kind of understand now. We've recently written a review a few months ago about this phenomenon, and I think that our understanding has come pretty far from this idea of like different sources of Barren plateaus to sort of like a more unified perspective of Barren plateaus. But for now, I'm not going to get too much into those details. This is not a Barren plateau specific talk, but I do want to mention some sources which might be good for you to know. So one of them might be my parameterized model. It's too expressive. And let me define the expressiveness of a model by how many unitaries it can produce. You put different sets of parameters in, you get different sets of unitaries. And one question that you might ask is, okay, given the whole unitary group acting on my Hilbert space, what is the set of unitaries that I can cover? Maybe this is this blue region. And then maybe I'm trying to solve problem A, whose solution unitaries lie here. I'm also trying to solve problem B, whose solution unitaries are here. And you might be like, this is great. My model can solve both problems. So I don't have to change model as I change problems, because it contains solutions to the two of them. And while this seems very good, it has the problem that you can rigorously prove that this is going to have a Barren plateau. And this is a form of the way that I see this, no free lunch theorem, whereby you can't have one model to rule them all. You can't have one circuit to rule them all. That is not possible. And the problem is that even if you don't realize it, this algorithm that you might be using is just as powerful as just like random hardware efficient ansatz, or just using the most powerful ansatz that you have. It's really easy to make a small modification to a circuit. You're like, oh, let me just put this gate here, uncorrelate these parameters, and now you have a universal model. So this is a very big problem. Quantum algorithms are very expressive in general. And something that we were wondering here is, okay, maybe we don't want to use a model that is too powerful. Maybe we want to put some inductive biases in it. Maybe we want to restrict its search space so that now maybe this model can only solve problem A, it cannot solve problem B, and we have reduced expressiveness, and maybe we can mitigate Barren plateaus. So the question is, will this have Barren plateaus? Yes or no? And it turns out that it depends. But as we will see, you can have Barren plateaus in extremely inexpressive and shallow circuits. So as an example, as we will see here, you can, and it will depend on properties like the loss function or whatnot. But for instance, consider this problem. I'm going to define it for you. You start in the old zero state. You're going to send it through this circuit, which is just independent rotations around the y-axis, and you want to recover the old zero state. That's it. That's the task that you're trying to solve. Well, if you're clever, you might be like, well, just don't do any rotation. Set all your angles to 0. So we know that there is a solution, and we know that I can start in the 0 state and get to the 0 state. But that's not it. We want to do this via training. So you might be like, OK, let me define a loss function. Let me just compute what is the probability of being in the 0 state, so that my cost function is 1 minus the probability of being in the 0 state. If you do this, you're going to see that as you increase the problem sizes, this is going to start having a Barren plateau. And not only that, Barren plateaus come accompanied with this phenomenon, which is called narrow gauges, which is that the volume in parameter space that corresponds to your solution shrinks exponentially. Because you might be saying, OK, maybe just initialize a bunch of times, and maybe you'll just happen to stumble into the minima. Or just do a swarm method, where I'm just going to throw a bunch of points in the landscape. Well, the probability that you actually hit this is also exponentially small. So this kind of trivial and innocuous-looking problem, it doesn't even generate entanglement this ansatz, but it has a Barren plateau. OK, but you might be like, this is not the only way of defining a cost function. What if I define a cost function where this looks complicated, but all that it's doing is check what is the probability of the first qubit being in 0, add to the probability of the second qubit being in 0, do them all, and average? Well, we know that if individually each qubit is in 0, they're all in 0. So I can use this loss function, and it turns out that it doesn't have Barren plateaus. And you might be very happy, because you might say, oh, maybe local cost functions work. But as we will see, this has some caveats. And again, this is just the narrow gauge phenomenon. So you might say, OK, what if we go beyond this toy model problem? When do we think we're going to have Barren plateaus or not? Well, we have this paper where we consider this extremely popular architecture. Let me just call it a hardware efficient ansatz, but it's just, I have qubits. I'm going to assume that in my device, I can only connect neighboring qubits. So I'm just going to apply gates between each qubit and its neighbors. I'm going to try to pack as many gates as I can per layer to parallelize. So you will end up with this architecture almost very naturally. And this box is just some gate. So you can ask the question, when will this have a Barren plateau, and when will this have a Barren plateau? Well, turns out that the top one will always have a Barren plateau, independent of how many layers you're doing, even at one layer, and kind of the intuition is coming from the previous. Whereas this one right here, it has a transition where log n layers is trainable, then you have some transition regime, and then some Barren plateau regime. And don't get too attached to all of this, because we will see that this actually doesn't turn out to work even if you don't have Barren plateaus. Because we have really spent quite a bit of time thinking about Barren plateaus and trying to understand why this phenomenon occurs, why this phenomenon doesn't occur. And for me, I think that the thing that made me realize, or maybe this is my own personal interpretation, and this is up for debate, is that Barren plateaus are just a curse of dimensionality. And how did we get here? We had enough architectures that had Barren plateaus, and we just write them all in a whiteboard, and then we stare at it, and we ask, what do they all have in common? So eventually, we had enough data to start looking at the trees, start looking at the forest, and we realized that this is our interpretation. And in hindsight, it's almost trivial. It's almost trivially true, because let's consider the loss function. We said that we were just going to compute things that look like this, and this is just the Hilbert-Schmidt inner product of two operators, some quantum state rho and some measurement operator O, that belong to the set of bounded operators in our Hilbert space, right? So the loss function is expressed as a similarity measure between two exponentially large objects in some vector space, which is B. And this, since day one, since the VQE MacLean paper, we should have been like, wait, this is a bad idea. Because we know that under very, very, very mild assumption, if you have an exponentially large space and you take two vectors, unless they're extremely close, their overlap is bound to be exponentially small and concentrated. So this, I think, is kind of like the order zero understanding of Barren plateaus, which is that they are a curse of dimensionality. And this thing that we wanted to use, which was the exponentially large feature space of quantum systems, well, it turns out to be the thing that is actually very, very bad. And I haven't even gotten into local minimas. This is just Barren plateaus. So again, remember that this is just a part of a much larger set of issues. And we can ask the question, well, how do we know if we're going to have a Barren plateau or not? Say that I give you an architecture, and I ask the question. Something that you can do is just think about the Heisenberg evolved measurement operator. So now, apply the unitary to your measurement operator, and just ask the question, as I change the parameters, where can this guy go? And as we will see, for classes 2 and 3, this is going to be the running theme. We're going to try to analytically compute this for different problems. So we want to see if this can explore an exponentially large subspace. And something that we could do is to see where this is contained is we just take a basis, say the Pauli basis, we just orthonormalize it of all operators, and we just compute the inner product, because this is going to tell us how spread my measurement operator is. Well, for global unitaries, it's not hard to convince yourself that if I start with a measurement that is kind of like X acting on all the qubits or some global measurement, if I apply this, I'm going to be able to move in an exponentially large space. And this is true even at the single rotation level, which is the issue that we've already had. You can take here, imagine that this is X, this is a rotation around the Y-axis. This can take me to 2 operators here, times 2 operators, times 2 operators, blah, blah, to the n operator space that we can explore already with global measurements and single qubit rotations. So this is exponential. What about this? Well, it's the same problem. This is also going to be exponential. What about this guy? Where can the backwards evolved measurement operator go? Well, it just stays in this light cone, because if I start with a measurement operator here, these gates are essentially doing nothing, and I can only propagate. So if I have a logarithmic number of layers, if this is L, this is 2L qubits in my backwards light cone. So if this is logarithmic, this is also logarithmic, And how many operators act on logarithmically many qubits? Polynomially many. So this lives in a polynomial subspace. So again, here we can see that one can reach a very small number of operators when we're acting on a very small number of qubits. This kind of shows the importance that even the same circuit with different measurement operators and different input states can have Barren plateaus. Because what happens if I now do a local measurement, but my initial state is going to be too entangled? It satisfies maybe a volume law of entanglement, where all the expectation values on log n qubits are going to be exponentially concentrated. So even this, when you have too much entanglement in your initial state, is going to be untrainable. So again, we need to be careful about proving absence or presence of Barren plateaus, especially absence, because a circuit with different inputs and measurement operators might lead to issues. So for now, we were at this point, and we wanted to ask the question, how can we solve the problems? Can we actually solve all of those issues that are appearing from Barren plateaus? And once we identify where most of the issues are coming from, which, as we said, is just a problem that we have this exponentially large space, and we might not be handling it properly. And we already know that if we explore too much space, this might have a Barren plateau. So we say, well, let's systematically restrict the model search space. And how do we do this? We thought that we could do this by putting symmetry information about our problem at hand into the model as inductive biases. And this was maybe a year and a half, 2 years and a half ago that we started working on this. We got to this thing that we call geometric quantum machine learning, which is just how to put symmetries into quantum machine learning models and try to show that this will avoid some of the issues. And this was great. We put out a tutorial on representation theory, we gave theory, and this paper, we found the holy grail of properties. It's a model that doesn't have Barren plateaus, no matter how deep you go, or what is the measurement operator that you have. There's still some dependence on initial state, but this is normal. It will over-parameterize with very few training points. It can generalize really well with very few data points. So I think that this is a point of my life that I like to call happiness. We're like, we've done it. We've beat Barren plateaus. But again, if something seems too good to be true, it probably is. So how do we avoid Barren plateaus? We have all of these models for which we can individually prove heuristically that they don't have Barren plateau. So what do they all have in common? How do we actually avoid Barren plateaus in all of these architectures? Well, again, hindsight is 2020. They all do exactly the same thing. They take your search space and they just restrict it to a polynomially small subspace. And this we actually found to be a true statement. Absence of Barren plateaus means you are initialized in a polynomially small subspace. So we just took all the examples in the literature of circuits that don't have Barren plateaus, and we've shown that this is true. We can actually identify the polynomially small subspace that you live in. And something that is fun is that it is the actual proof of Barren plateaus that allows us to identify these subspaces. Because when you do Barren plateaus, you're trying to keep track of what are the components of your Heisenberg evolved measurement operator that will lead to large gradients. And it turns out that there's always something that lives in some very small subspace. So this was a problem. This was really, really a problem, because the next logical question that arises is, okay, we understand Barren plateaus, curse of dimensionality. We're avoiding them by restricting to a polynomially small subspace, but now this is probably going to be classically simulable. And this is the question that we started exploring, which was, if we have a model that lives in a polynomially small subspace, is this classically simulable? Because if it is, then that means that we shouldn't be running quantum circuits in a quantum computer, because everything that they can do, we can just emulate their action on some subspace of interest, and then that's it. And we can, if we can do this in polynomial time, then parameterized quantum circuits and their processing information capabilities are not going to be useful. So this is something that we've done. We've conjectured that problems in known polynomial subspace should be classically simulable, and this is going to be very important, so I'm going to get to that in a second, which is that quantum computers might still be needed, just not to run parameterized quantum circuits. And this, previously, stuff that I've said has been, we can rigorously prove. This is just something that we've kind of proposed. We've said these models should be classically simulable with these methods. Of course, the reviewers were like, well, how do you know that this is classically simulable? So now we're tackling one by one at a time and showing that this is actually true. So if we take a step back at this first hour of the lecture. Oh, yes, you had a question? Oh, you were like, we can ask the question, what did we actually prove in all of this story of 6 years? Well, I think that the first thing that we've proved is that working in quantum machine learning is a roller coaster of emotions. It really is. You think you've solved a problem, then you have it. And then you think that you're doomed and you find something, but it turns out that it doesn't work. So, you know, it's definitely exciting and interesting, but emotionally exhausting. So now going into more seriousness, what we've proven is that the devil is in the details. Before we had this computational paradigm where you give me a problem description, the Hamiltonian of interest, I put this into a parameterized quantum circuit in a quantum computer, make measurements, estimate expectation values, give this to a classical computer, optimize, and try to solve the problem. And here is the measurements in our quantum computers, and maybe a little bit of classical post-processing that is estimating the loss functions. So let me note that even here, we're not exactly computing the loss function. We're estimating it via finite samples. So if you read our paper, we call this quantum simulation because the quantum model is also simulating the landscape. It's not actually exactly giving you the value. That's just not possible. But now we have this new computational paradigm, which is I will give you the problem description, and I will allow you access during polynomial time to a quantum computer. You can make measurements, store those in a polynomially sized memory, and after that initial data acquisition phase, you're not allowed to use the quantum computer anymore. And your goal is to use the data that you've acquired during this first initial state in a classical computer to estimate the loss function. And this is the type of dequantization that we're talking about. We've shown that most Barren plateau-free models are here. We still need a quantum computer to get data. We're not running parameterized quantum circuit here. That is completely unnecessary. Their action is done in this classical computer. But we do need to get some measurements from a quantum computer. And this is also going to be central in the talks for tomorrow and the day after of the interplay between these two things. Then you might also be saying, OK, but this starts sounding weird, because I'm pretty certain that I can come up with some cost function that is not concentrated and yet is not classically simulable. Of course you can. We know that you can, and we actually propose one. We've defined some very artificial cost function that embeds Shor algorithm in it, and then it cannot be classically simulated, because otherwise a bunch of cryptographic assumptions are going to break. So is this practical? Can we use this kind of like Shor embedded quantum machine learning model for something useful? I don't know. I don't think so either. I don't know. But this is something that people have always said, which is like, you can always put Shor into something and then call it a quantum advantage. For me, this is not it. This is not useful. So I'm talking about models that people are using nowadays to try to solve problems of interest. But more interestingly, there's this very nice paper by the Google group. It's called The Power of Data in Quantum Machine Learning. And what they showed is that if you take the class of algorithms that a classical computer can solve in polynomial time, BPP, the class of problems that a quantum computer can solve in polynomial time, BQP, and then you ask the question, what happens if I give classical algorithms measurements or data from a quantum computer? Well, it turns out that you get this class, BPP-SAMP, which is strictly more powerful than BPP. So this is great, because maybe we don't have to do information processing in the quantum computer. Maybe we just need to use the quantum computer for what is good. It's preparing some non-classically simulable stuff and then analyzing that in a classical computer. Of course, what is the best set of measurements that you need to do, how to efficiently extract that information are extremely hard questions, and they're task-dependent, but this, for me, is extremely exciting. And the fact that Barren plateaus kind of took us here, naturally, was really amazing. That the fact that we've converged to this point from like pure quantum information theory from Robert Huang and Preskill's group, and quantum machine learning and trying to navigate all of this mess, we kind of converged to the nice point. And I think that this is very nice, and it probably is telling us something very deep, which I don't yet quite understand. So also, there's not a single notion of simulation and dequantization, because we care about quantities that kind of look like this, and we can define different notions of classical simulability. So for instance, we might have some average case simulabilities, which is if I give you a random set of parameters, you should be able to estimate the expectation value with very high probability, and this has to be smaller than epsilon. This would be an average case simulation. But maybe you're like, well, this is not useful, because maybe this can just approximate the loss function whenever I randomly initialize my model, which is a random point in the landscape, but random points in the landscape are not useful. They're not representative, they do not contain solutions, so maybe I want to do simulation for all points. And here you can add with high probability if you want, but the idea is that now you just remove the average, and you do this one right here. But also, you can be even more pragmatic and say, well, I don't care about point by point my landscape being epsilon close with very high probability. If you give me data from a quantum computer, and I can do some simulation of a loss function, and I can train on that, and I can get a solution that performs as good as the one that is solving the problem using a quantum computer, then this is also a simulation, and this is also dequantized. So there's actually all of these different notions of classical simulability, and their interplay that I think we can explore. So for instance, the first thing that we've been able to prove is that average case simulability, it's easy. It's almost trivial. Give me a circuit, random quantum circuit, which also means like you're randomly initializing it or whatnot. Well, estimating to precision epsilon with high probability can be done in polynomial time very, very easily. And this uses this idea of taking the Heisenberg measurement operator, the Heisenberg picture, where you take the measurement operator, you Heisenberg backwards evolve it, and whenever this becomes of too high bodiness, you just drop that path away. And it turns out that this is an amazing approximation of most quantum circuits. Now, is this useful? I don't think so. I don't think this is actually giving us any form of usefulness for solving a task of interest. So that is a caveat that I would say about this paper. It's interesting, but it is definitely not practically useful. So there is not much that we can actually do by running this algorithm and trying to use it for quantum machine learning. So the non-average case, that's going to be in parts 2 and 3. And let me give you a brief outlook of this part of the talk. And this is not the end. I still have some stuff that I want to talk about. So bear with me for just an additional second. What have we done? The first thing that we saw is that creating a variational algorithm is easy. Almost too easy. And I think that this is the problem. But again, you could push back and say that classical machine learning is easy too. And it's almost too easy. But again, the problem is that classical machine learning works. So who cares if it's too easy? Probably you can get a Nobel Prize in literature using machine learning. So again, the problem with quantum machine learning is that we have all of these issues, the Barren plateaus, that are not going to appear whenever you're looking at your problem in small instances. So even when you have a variational algorithm that it works, we need to make sure that there is not some assumption that you're throwing in there, like maybe you're not using finite samples. And that's what's making it work. So how can we guarantee that the quantum computer is doing actually something useful, and more importantly, something that a classical model cannot do? So in the second part for tomorrow and Wednesday, here we are going to understand why this circuit doesn't have Barren plateaus and classically simulating it, showing that the first part of our paradigm, VQE, was classically simulable. Nothing interesting can be done there. And then we're going to take quantum convolutional neural networks. We're going to learn about Weingarten calculus. And hopefully, this is the one that requires quite a bit more math, but we'll see if we manage to get there. Also, dequantize this guy. So all of that pipeline, all of those nice papers that we can put out there, they're actually all classically simulable. You just need to really look under the hood, and they're not classically simulable in average. We can actually emulate the whole training and use a quantum classical simulation that will perform as well as the true quantum model, even under more restringent conditions. Something else that we will do, well, we talked and we touched base on some of these guidelines today. So global observables are bad. Deep circuits will have Barren plateaus. Too much entanglement has Barren plateaus. Who knew about those before? Okay, that is not a lot of people, but for people who knew about them, you need to know that those are false. And in fact, they are false because they were derived for specific architectures where it was shown that for this architecture, under these conditions, global observables don't work. For this architecture, Under these conditions, two entangled states don't work. But those are not general guidelines. QML is extremely, extremely subtle, but we will actually find what is the correct set of guidelines that we should learn for every model. So I think this is perfect because I still have a little bit of extra time to introduce something for next class. So now we will start talking about groups. And this is going to be the preliminaries of what's going to be needed for tomorrow's class. So maybe I'm going to try to go slower here, because for people that are not familiar with groups and representation theory, if you don't get this, then we can chat in the afternoon. And this is why I wanted to get to this point, so that if something isn't clear about this first part of the introduction, let's chat, because we're going to build on top of that during the next 2 lectures. So this needs to be solid. So math, what is a group? Well, a group is a set of objects and a binary operation that takes 2 objects from that set and returns me another object from that set. And it has certain properties. Like, for instance, I'm going to do something that I shouldn't do, which is talk about a representation here. But we're going to get to that in a second, which is that let's think about rotations in a plane and why those form a groove. If I give you a cat and a rotation by the angle θ1, you get this cat. If I give you another rotation by θ2, you get this cat. But you can also apply this multiplication first, and that's going to give you a rotation by θ1 plus θ2. So those 2 are equivalent. I take 2 objects in the group, 2 rotations, multiply them, I get a 3rd rotation. Then properties of a group, multiplication is associative. So the order in which I implement them doesn't matter. And you can actually see this from here. If I were to rotate this first or this, and then I put a 3rd rotation, the rotated cat is going to be the same. There is always an identity element. There is this element E that belongs in the group, such that if I multiply it by any other element, I get itself. And in this case, is don't do any rotation or a rotation by 0 angles. Then we have inverse. For all the elements in the group, there exists another element that is also in the group, such that their composition gives me the identity. In this case, that would be a rotation by θ1, a rotation by minus θ1, and their composition actually leads to the identity. Whereas I'm now no longer convinced that just putting symmetries in quantum machine learning models will be the answer to solving all of our problems. We did write this tutorial that talks about a gentle introduction to representation theory from the optics of quantum machine learning. So if you've sometimes found that math books can be quite heavy, I would recommend this article, not because I wrote it, but because this student wrote it. And their idea was, let's try to write something that is digestible for people in our community, which maybe don't want to go and they don't want to read like Hall's book or Goldstein, because that might be a little bit too much to begin with. So this is pretty much what you can expect in this article right here. Now, that is the general definition of groups. Groups can be discrete. So that means that they're composed of a finite set of elements. The simplest group that we can think of is this thing right here, Z2. And at this point, I'm going to define Z2 as containing 2 elements, and I can define their composition table. Like, I already know that the identity times anything else should be that thing. So E times E is E, E times sigma is sigma. This we get by associativity. And then we ask the question, how do I know that sigma times sigma is E? Because everything needs to have an inverse. So the table kind of just completes itself. Now, these are abstract objects. Don't think about this as matrices or something like that. They're just abstract objects. And this thing right here, which is called the Cayley table, is in a way the fingerprint of our discrete group. So if I give you a discrete group, you just build a table of how things are composed among each other, and that is going to tell you what is the underlying group. We can also have continuous Lie groups, and we're going to work with Lie groups. For people that don't know what a Lie group is, they're manifolds that are also differentiable. So I can define things like derivatives over them, and that connects Lie groups with Lie algebras, and we're going to see more details about this tomorrow. So in this case, we can have our Lie group as U2, and we might say, okay, what is the equivalent of doing this? Can I just take all the elements of SU2 and multiply them and try to characterize my group through this. Well, the problem is that you cannot. It's continuous infinite number of elements. So a common theme, and this is something that we're going to see tomorrow, is that whenever you have a problem at the Lie group level, you pass it to the algebra level, and then you come back. So the associated Lie algebra is just small SU2. And this guy right here has 3 generators. And the Lie algebra is defined by a set of objects and an element, which is usually called a Lie bracket, which takes 2 elements in here and gives me a linear combination of these guys. The fact that I can do linear combination already implies that, or kind of hints at the fact that this is a vector space. So for SU2, I can characterize this algebra by taking the elements, applying the Lie bracket, and seeing what is the formula that I get. Again, this is abstract at this point. This shouldn't mean too much. And this is the fingerprint for this Lie algebra. And once you've solved everything at the algebra level, you can characterize SU2 by exponentiating the Lie algebra. And this is the exponential map that does pretty much all the connections between Lie algebras and Lie groups. So I hope that this wasn't too terrible, because now we're going to talk about representations. So thus far, I've been very strict about saying groups are abstract objects. They don't have any instantiation. What we're going to usually do is we're going to have a vector space V, and we're going to have a set of objects that kind of behave like groups. So in this case, what we're going to have to study is representations of a group that tells us how a group acts on a vector space. So a representation is something that takes elements in the group and gives me invertible linear maps in this vector space. If you're not familiar with GLV, just think about it will give me a unitary. Now it's a matrix that is dimension V times dimension V that is unitary. I'm swiping some stuff under the rug here for the mathematicians, like I'm assuming that the group is compact and it will behave so that it admits a unitary representation. But for now, let me just assume that our representation is going to give me a unitary. So let's consider an example. What if I give you a single qubit Hilbert space, C2? Can we find different groups that act on this vector space? We already know that we have the Z2 group. And what if I give you this representation? It maps E to the 2 times 2 identity matrix, and it maps sigma to the Pauli X matrix. You build their composition table, and you see that they match. So that means that bit flips are a representation of Z2, because their Cayley tables match. They satisfy the fingerprint of the discrete group. What if I now give you Pauli operators, X, Y, and Z? I multiply them by Y, and I allow you to do any combination. I'm missing some i's here. So if you do this, you're going to see that they satisfy this commutation relationship, which actually turn out to be the same as these abstract things. So Pauli matrices, X, Y, and Z, form a representation of SU2. I think this is a solution to one of the exercises, so I'm a little bit sorry about that. But the exercise is actually a little bit different, because you still need to get to this point. You're starting with exponential of things, and you need to get to the Lie algebra level. So the exponential map has to appear somewhere there. So I've just given you the second step, not the first step. And again, this is the exercise. Actually show that this is a representation of the group SU2. All right. So this is all very nice, but now what does representation theory actually do? Well, one of the questions that it's going to ask, and this is going to be the central question, is if I give you a group that is acting on a vector space, does it create invariant subspaces? Is there going to be some subspace, which we're going to call W, which is inside of our vector space where we act, such that if I take a vector in this subspace, and I multiply it by any element of the group, I remain in this subspace. So that means that the subspace is closed under the action of the group. It's an invariant subspace. I cannot take any vector and go anywhere else. I'm just stuck in this W by action of R. And what we're going to see is that this idea of invariant subspaces is very intimately related to block diagonalization. So what does block diagonalization means in the language of matrices? And I'm a very visual person. So if I tell you this is block diagonal, I'm like, why? I kind of need to see it. So here it is. If I give you a matrix A, and the identity matrix, and I just tensor them, you kind of get this matrix right here. So you can see that this has a block diagonal structure. You have a block here, then zeros outside of the diagonal, and another block here. And if you think about this as a vector space, that means that if I give you a vector that lives here, and I multiply by a matrix that looks like this, I will stay here. So invariant spaces are very intimately related to block diagonal structure. And what we're going to say is we're going to start introducing some language. So don't worry if this sounds complicated. But if I give you a representation of a group and you don't have any invariant subspaces, we're just going to say that this is irreducible or an irrep. So it's nothing too complicated. It just means that there is no invariant subspaces. So essentially, the question that we want to know is, if I give you a representation of a group and I take some element, does there exist a basis? And this is very important. There is a change of basis from here to here, such that my matrix is going to decompose in this way. Because if it does, it has block diagonal structure. So here we can see that this means that I have this block, which I'm just going to call R lambda, where lambda just determines what are the different irreps. And multiplying by identity just means this. I have the same block repeated m lambda times. And then you might have this direct sum. Well, maybe you don't remember what direct sum is, so let's do it right now. If I give you a matrix B, and I do this guy right here, and I direct sum B, you get this guy right here, which again has block diagonal structure. So we can see that this is essentially what we want to try to study. If there exists a change of basis, well, my representation is going to look block diagonal. So let's consider some examples. Let's try to see if we can block diagonalize SU2. So I give you a group, then I have to give you a vector space and a representation. So now this is abstract group. So take the vector space to be the Hilbert space of a single qubit, and I'm going to consider the standard or the defining representation, which is you get a matrix and you get itself. I know this kind of looks weird because I've said don't think about this as matrices, and here I'm kind of telling you, well, they are matrices. But yeah, this is something that is odd about representation theory and fundamental representations. But it's just 2 times 2 unitaries. And now you can ask the question, if I give you a single qubit Hilbert space and I apply unitaries, will they have invariant subspaces? Would you expect them to have invariant subspaces? Is there a state that I cannot map to any other state via unitaries? If I give you a single qubit state, is there another state that I cannot reach by applying a unitary? Yeah, exactly. There's no. And you might be saying, all right, maybe just let me think about this. I'm going to sample a bunch of unitaries uniformly from the unitary group and try to find if maybe there is one that is in some change of basis, block diagonal. Well, they're not, and this is because it is a 2 times 2 irreducible representation. So V, the action of R on V is actually irreducible, and we can prove this with a little bit more care. Now what happens if I give you 2 qubits, so this is the Hilbert space of 2 qubits, and I give you this representation. So in circuit notation, this would kind of mean just this. So apply the same unitary to both qubits. The question is, do these have invariant subspaces? Okay, people are saying yes. And we can, I'm a very visual person. I start sampling a bunch of unitaries, tensoring them together, and I'm like, well, there is no subspaces there. But of course, we need to be careful because there exists a basis where these guys are block diagonal. So if I take the Bell basis, and I do the change of basis, your matrices are going to look like this. You're going to have a 3 times 3 block corresponding to these guys, which is what people call the symmetric subspace, because these guys are invariant on their permutation of the qubits. And you have a 1 times 1 subspace, which is the anti-symmetric subspace, where these guys, if you permute them, you get a minus sign. So in this case, what we would say is the representation, the 2-fold tensor representation of SU2 in C4 is not irreducible. It has a 3 times 3 EREP. You can prove that this cannot be further decomposed, and a 1 times 1 EREP. And that means that my Hilbert space is going to decompose into this symmetric and anti-symmetric component. Something that I'm going to keep highlighting is that the smallest representation of a group that is non-trivial, this is kind of like a trivial representation, because you can actually test this. This is a lot of fun. But if you apply U tensor 2 to the anti-symmetric state, you should get itself. It is an invariant subspace. It's the unitaries act trivially. There might be a phase, now I don't remember. We can think about other representations. We can think about their adjoint action. I give you another vector space. Now I give you the vector space of operators acting on Pauli's. Now I need to think about, well, operators acting on single qubits. A basis of this vector space, this is 2 times 2 matrices, are all Pauli operators. And we can take the adjoint representation, which kind of just looks like this, which just means conjugate. And we can ask the question, does it have invariant subspaces? And again, how do we answer this? We just take a basis, and we conjugate all the unitaries, all the elements of the basis with unitaries, and we ask, where can we go? By looking at this, would you think that this is irreducible or not? What happens if I take the identity and I conjugate by any unitary? Can I get to X, Y, or Z? Oh, I get stuck in the identity. So this is an invariant subspace. And then it's not hard to see that you can take any Pauli, conjugate it with unitaries, and get to any other Pauli. So that means that those three on themselves form another invariant subspace. So now we can see that the adjoint representation acting on this vector space of bounded operators on C2 is not irreducible, and it decomposes like this. You have, again, a one-dimensional space where you act trivially. You can see it here, which is that the action of every G is just the trivial action. It does nothing. So this is important, because what I want to say is that representations have a lot of properties to them. One of them is there always exists a trivial representation. I can always give you a group and a trivial representation where everything gets mapped to the identity and then nothing happens. But then if you ask the question, what is the next non-trivial representation? Here we saw that this is 3 times 3. In the previous example, we found a 3 times 3, but here a 2 times 2. So something that is going to be very important, and this is to keep in mind for tomorrow, is that the smallest non-trivial representation is of the size of the group. And that is going to be very important, because that means that very large groups cannot have small invariant subspaces. If you have a group that is exponentially large, its smallest subspace has to be exponentially large if it's non-trivial. And if it's trivial, then nothing interesting happens there. So this is going to be important. And I think that with this is the last slide that I wanted to cover today. For tomorrow, it's essentially going to be pen and paper. I'm going to start with, I might still use some slides, but Mondly is going to be working here. And we have, I think, still 7 minutes, so I'm happy to take any questions that you might have.
It's just to ask questions, but I studied a little bit quantum machine learning. I'm theoretical physicist, but one postdoc after Russia was at IMPA with quantum machine learning, and there was a paper, maybe you know, it's a very famous one, by IBM. It was about quantum convolutional neural networks, and they use Fisher information matrix there, and they claim that, oh, actually for 27 IBM qubits, we see a better results and so on. They actually talked about entanglement, so that too much entanglement is kind of bad. And But when we started checking, we had some questions, and so
We
we
too.
got many doubts. And then I also talked to another researcher in Germany. He also studied quantum machine learning, and he also was like hesitating about the power of quantum neural networks.
Yes.
Yeah. So the question is, when people use, so first I think the geometrical approach is the best. It's like, so that's really cool. It's just from the perspective of biology. If we think about how our brain is working, it's geometrically optimized, right? And I think we should move in that direction. So when people use like this Fisher information matrix to see this Barren plateau landscape with eigenvalues distribution, okay, so what's the use of it? So they can do it, and then what? Because I didn't see kind of, you at least showed that some tables with like analysis of specific algorithms, and even gave us approach, this geometrical approach. So, but that paper didn't give that. They claimed something big, but...
So here's the thing. I need to be careful what I say because this is recorded and it's going to go on YouTube. All that I can say is that we were very surprised by that paper too. We got a student, we checked all their proofs. The proofs were correct. Then I had a poor student review all of their code. And I can tell you that, let's chat later, but let's just say that the results are not correct. The results are definitely not correct. What they're claiming is it's an artifact of a bug in the code.
I'm sorry. I have Psycom channel. I'm open. I think science should be open. And
Yeah.
when we started checking the plots, and they built the distribution of eigenvalues,
Yes.
and they were comparing some classical convolutional neural
Yes,
network
yes,
with
yes.
quantum.
Yes.
What they use, guys, so this is for every undergrad first-year student, they use different axis scales.
Yes. Yes.
Like they, oh, look, the distribution here is so like good, like you have so many good ones, and so this means something, but it didn't mean, because for one they use from 0 to, I don't know, 1, the scale, and for quantum or something, they use from 0 to 20 something. So it was, even from basic perspective, not really good. Also, they didn't mention what convolutional neural network they use. And my question, fundamental, how can you even compare classical convolutional neural network to quantum?
Yes.
Like in terms of mapping, there are some rules.
It's a really hard question, and I was discussing yesterday, last week this, and I don't think there's an easy way to compare quantum and classical, by no means. For me, this is why the best that I can do is say, oh, I found a classical algorithm that is maybe not some classical neural network with the same number of parameters. I just found a classical algorithm that uses the same information and solves the problem. This is the approach that we're going to take. But yeah, it's not hard. And just another point about those plots, it's not even that. Their eigenvalues are, they use a normalized Fisher information, and they don't mention this. They multiply their eigenvalues by 2 to the n. So that means that their smallest eigenvalue is actually exponentially small, but because they renormalize multiplying by 2 to the n, everything's order 1, which kind of doesn't work. And we actually wrote a whole paper on why this doesn't work, because people were saying, if you have an exponentially small quantity, multiply it by 2 to the n, and you're fine. And we're like, whoa, no. Okay, let's discuss when I'm not being recorded. Yeah. I think it was mentioned here. It's called subtleties in training quantum machine learning models. I can give you the reference offline. Yeah. We can. I'm gonna be here all week, so I'm happy to chat.
So general relativity. Can we use quantum machine learning to simulate general relativity problems? You're an expert, so...
So if you're asking me...
You have manifolds, so you know
If
geometry
you're asking
too,
me
so-
about simulation
Yeah.
of relativistic quantum mechanics or field theories or stuff like that, that is a very different question of using quantum machine learning. Quantum computers can be used for simulation of field theories and even relativistic ones. There's this paper by Preskill where they actually show that the simulation of field theories is BQP complete. So that means that if you could simulate that field theory that a quantum computer can implement, you could simulate everything.
But this is kind of easy with quantum field because Ising model and all of this, no, it's kind
Yeah.
of related, condensed matter, it's, yeah. But I was asking about general relativity and like people used AI, machine learning. The question was, because they asked me too, some researcher from like United States, they asked if we can apply quantum computing, but let's say quantum machine learning specifically. So yeah, that's the question.
My opinion is that unless you have a really good reason, I don't see why or how. And this is going to be my answer to
But that's
pretty
good
much
one.
everything.
So you're saying basically we have to categorize the problems to see if
Yeah.
we even need to apply quantum machine
Correct.
learning to this problem. Okay.
Yes. For the specific case of relativistic quantum mechanics, it seems to be a really hard problem. I have a student that is very interested on that. We haven't found a good way. I wouldn't do it with quantum machine learning. I would just think about like traditional algorithms, traditional programming approach, but not generally quantum machine learning. That would be my thought. Because even the discretization of the problem enough so that a quantum model can learn it seems non-trivial to me. And if you want to have a mesh that is fine enough, you're also going to encounter problems of the Lorentz group is not compact. So you can boost things and augment energy kind of like ad infinitum. Unitaries are not well suited for that, so you're probably going to have to do some blocking coding to try to get this non-unitarity. You're likely going to have to run into imaginary time evolution to be able to, again, get rid of the unitariness of parameterized quantum circuits. So already, if you ask me, what can we do with just Lorentz group? Forget about relativistic quantum mechanics. Lorentz group in quantum computers, it's a really hard question because they're non-compact groups. And this is why I said like everything here is compact. Yep. I need to see something that will convince me. Yeah. I'm not convinced that quantum machine learning has a practical application just yet. But again, I'm playing devil's advocate here. I want people to prove me wrong. I'm going to be the naysayer. I've accepted that I'm one of the villains of this story. I'm happy with that. Right. I mean, differential equations and quantum computers get kind of nice. Nana Liu has a lot of really nice papers on Schrödingerization, and they've applied that to fluid motion equations. But again, not quantum machine learning, traditional quantum algorithms. Exactly. And sorry, I think there was a question, but we can keep chatting in the break.
First of all, thank you for the talk. It was very enlightening, pretty funny too. What I wanted to ask was, I guess I was a bit inspired by the question of simulating field theories in quantum machine learning, but not for field theories because we have for classical neural networks those so-called neural network quantum states, which are ways to represent quantum states as neural networks. Is there an analog, or do you think there could be an analog for quantum neural networks? And if so, would there be like any advantage to it, or are they just the architectures just too different?
I don't know because quantum neural states are something very different. You're talking about Giuseppe Carleo's work?
Yeah.
Yeah. No, that is very different. That's used to representing families of states very efficiently, and that works extremely well. Quantum neural networks, the problem is that they're unitaries, so you need to start already defining what you mean by if something similar would happen. If you think about the question, will some states that are prepared at the output of parameterized quantum circuit admit an efficient representation? That is likely going to be problem and circuit dependent. But I don't know, I haven't seen a lot of this. Really.
Thank you.